Okay, so here is a video. This is the second page of your notes that I gave you guys yesterday. So for those of you who are absent, they're in the bin, and then the rest of you should have them from yesterday. If you do not, then just take them on paper because I do not have any extra copies. Yesterday we talked about Bernoulli trials. So pause me and go ahead and right here write down the 3 things that are true about a Bernoulli trial. So pause me and then check your work. Okay, so Bernoulli trials have 2 outcomes, a success and a failure. We call them P and Q. And then P is the same for each trial, so your probability of success does not change. And then last but not least, the outcomes are independent. And remember that this has a loophole. If our population is greater than or equal to 10n, it's okay to have a little bit of dependence there. We have 2 types of Bernoulli trials. Remember, we have binomial and we have geometric distributions. So today our focus is going to be geometric probabilities, and we've already done a lot of this, so just kind of putting that definition to it and looking at different probability scenarios. So the first one says a baseball player has a probability of 0.3 of making a hit. What's the probability that his first hit will be his 4th at bat? So as always, we need to start by defining our distribution. So X is our random variable that we're looking at. So this is going to be our number of at-bats until we have a hit. And then right underneath it, I'm going to write P equals 0.3 because that's our probability of success. So going back to our probability distribution notation, we're going to say here the probability that the number of bats until we get a hit is 4, because that's the question that we're trying to answer. So that means that in his first 3 at-bats, so doesn't have a hit, doesn't have a hit, doesn't have a hit, so in other words 0.7 times 0.7 times 0.7 times 0.3 is going to give us our probability of 0.1029. We have done this before. So our actual geometric rules, P is the probability of success, Q is the probability of failure, and remember that we can also call this 1 minus P because P and Q have to add to 1. X is going to be the number of trials until the first success. So this is the main focus of a geometric distribution. And our notation is going to be the first success happening when X equals N, where this is the trial that first success occurs on. So here are our 3 formulas. None of these are in your packet. Let's assume that you should know them. So the first one would be the probability that your success happens on the nth trial. Well, that would mean that your first n minus 1 trials are all a failure. So just like the last one, it was our fourth at-bat was a success. So that means that the first 3, 4 minus 1, were a failure. So this is our general rule in conducting a geometric probability. The expected value is 1 over P. So for example, that would be something like saying, okay, well, the probability of getting a tails or a heads is 0.5 or 1/2. So how many flips would you expect in order to see a heads? Well, you would expect 2, 1 over 0.5. Or in other words, probability of success is 1/6 for rolling a 1. How many rolls would you expect in order to roll a 1? Well, 1 over 1/6, which is 6. The standard deviation is the square root of Q over P squared. So these are both things that you need to memorize. So very briefly, I think we'll come back to this actually and prove why this is the actual expected value using some of our XI PI formula that we're familiar with. So we'll come back to that a little bit later. Let's go ahead and try out a couple examples. So this is the one that we actually spoke about yesterday. So rolling a 6 to move on. So here are 2 probability distributions. This one is the actual probability. So yesterday we talked about the scenario of you're playing a game that requires you to roll a 6 to move on. So X was the number of rolls until we get a 6. So number of rolls until we get a 6. So we said it could happen on the first roll with a probability of 1/6. over here we have the corresponding decimal. We could get it on the second roll, which means we didn't get it on the first, but we got it on the second. That gives us 0.139. If we got it on the third roll, didn't get it, got it, that'd be 0.116, and so on. And this really does keep going. These do not add to 1 because we don't know that when that could happen. So we want to find the probability that you toss the die 5 times, meaning that we get a 6 on that 5th roll. Well, first of all, we have it right here as the 0.08, and that means that we did not get our 6 in 4 rolls, but we did get it on the 5th. And that's where that 0.0804 comes from. Our expected value, our expected number of rolls is going to be 1 over p, or 1 over the 1/6, which is 6 rolls. Our standard deviation is the square root of q over p squared. So in that case, that's the square root of 5/6 over 1/6 squared, which is 5.477. So now we have our basic statistics that go along with a geometric distribution as well. Let's go ahead and flip it over and take a look at the next side. Okay, we have a couple of examples on the second page. So the first one says the American Red Cross says that about 11% of the U.S. population has type B blood. A blood drive is being held at LHS. So although I don't ask you for it at the beginning, let's first define our random variable. So our variable in this case is going to be X, and this is going to be the number of people selected until we find someone with type B blood. Now the new thing here is we're going to say that X is geometric with a probability of success of 0.11. So this is really similar to our normal. So remember, like, we say something's normal, we say that X is approximately normal, and then we say the mean and the standard deviation. So similarly, we can use, we can say that X is geometric, and then really the only thing that we need, the only thing that we need for the mean and the only thing that we need for the standard deviation is really just knowing what P is, that probability of success. So this is also common statistical notation, just like a normal distribution. So that's what this stuff below is saying. Okay, so the first one says what's probably that the 10th person is the first one to have type B blood. So because we defined it until we find someone to have type B blood, we're saying here, what is the probability, writing of course our original problem that we're looking for, the probability that the 10th person is the first one to have type B blood. So, well, what does that mean? That means that the first 9 do not have type B blood. So that's going to be 0.89 to the 9th, because that's all not B, not B, not B to the 9th, times the last person, that 10th person, having type B blood. So right there you have your final answer of 0.0385. Same rule applies, and I try to set the best example I can for you guys, but round to 4 decimal places. Okay, the next one says what's probably that the third donor is the first one who does not have type B blood. So sometimes it's easier to always refer back to your variable. Sometimes you'll feel like you lose yourself in notation, or you'll lose yourself in trying to define another variable. So there's other ways to do it as well. So here I just said, okay, well, what am I actually looking for? And I didn't really worry about the notation as much. So this is what's probably the third person is the first one who does not have type B. So that means that the first 2 did have B. So that would be B, B, and then not B. So that's the actual probability that we're looking for. And here, each donor, because this is geometric, each donor is independent. So it's going to be 0.11 times 0.11 times 0.89. So that's where we get the 0.0108. All right, let's scroll down a little bit. What's the probability that they will get the first type B blood donor as one of the first 5 people? So here that means that we're saying that we're looking for you could get your first type B blood donor on the first person, or on the second person, or on the third, or on the fourth, or on the 5th. So in other words, another way to say that is the probability that the first donor will be less than or equal to 5, happen on one of those first 5 people. So we're going to go ahead and calculate all those probabilities. So this one would be your 0.11. This would be your 0.89 times 0.11. This would be your 0.89 squared times 0.11, and so on. Okay, so as always, we aim for some simplicity here. So rather than going through and adding up all 5 of those probabilities, sometimes it's nicer to have a little bit of a shortcut. So let me get rid of this. I'm just going to move it over to the side. All this stuff apparently. Okay, and rather than adding up each of those probabilities, it's easier to use our calculator. So geometric is a new type of distribution. So just where you find normal, in that same menu, you're going to find geometric. So we're going to go to second distribution or second vars on our calculator. And that's where we get normal CDF, but we do not want normal in this case. In this case, we want geometric CDF. So if you scroll down, there's binom, Poisson, and then there is geometric. There's PDF and CDF. PDF is dealing with one case. CDF is a cumulative that counts from the bottom up, and of course it starts with 1 because with a geometric distribution you cannot have 0 as an option. So we're going to select here geometric CDF, geomet CDF. And then your arguments, and it depends on your operating system, are going to be N and then P. So in this case, we have something that looks like geometric CDF, and then our N, oh, I lied, I'm sorry, it's P and then N. Otherwise, your calculator will get angry at you. So we're going to do 0.11 to 5. And that's going to calculate all those probabilities for you and give you that 0.4416. If you were to select geometric PDF, so if we go back up to the top in that same spot, rather than checking cumulative with the C, here we could do geometric PDF, and then once again we're going to do the P and then the N, and it will give you just that one case. However, I think it's silly to use your calculator in this one because it takes more time to type this into your calculator than just do the raw probability, which we're comfortable with doing. Okay, last but not least, what's the expected number of donors until we get someone with type B? So here we're looking for the expected value of x, which we just did is 1 over p, which is going to be 1 over 0.11, which ends up being 9.09. So we would expect to see 9.09 donors before we get that type B blood. Alright, so we have another one. I want you guys to go ahead and try this one out on your own. So pause me, do as much of this one as you can, and we'll check back when you're done. Check back and check all your work. On the population of consumers, 60% like a certain brand A of toothpaste, and we are going to randomly select some people to see what they like. So X is going to be geometric, and its center is just 0.6. We don't actually have to say shape, center, and spread because this covers it all. X is the number of people we interview until we find someone who prefers brand A. It's probably that exactly 5 people have to be interviewed. Well, that would mean that we're looking for the probability that X equals 5. So that means that the first 4 do not like brand A, and then that 5th person does. And so we get 0.0154. What's probably that it takes at least 5 people to find someone who prefers brand A? Well, at least 5 means that it's going to either happen on the 5th person or more. So meaning the 5th person, the 6th person, maybe even more than that. Excuse me. So whenever we see that at least, remember that we always like to do the opposite. So here we're going to do at least 5 means that this is the actual problem that we're trying to solve. The complement is going to be 1 minus. Now in this case, the complement picks up at 4. So the stuff that is not it is going to be everything below. So here and under is what is not the purple stuff, which is why here we have 1 minus probability that X is less than or equal to 4. And then here, in order to get this number, I did geometric CDF in my calculator with my probability of success being 0.6 and then my N being 4. 1 minus that and we get 0.0256. What's probably that it takes 2 or 3 people to find the first consumer? Well, that means the success happens on the 2nd or 3rd, which is 0.336. Or, in other words, 0.4 times 0.6 plus 0.4 squared times 0.6. And that gives you your 0.336. So that finishes the notes for today. I do want to go over where exactly the expected value comes from, so it's likely that we'll do that first thing tomorrow. Your homework is Math Excel. Have a great day.